packet pushers.
Welcome to the IPv6 Buzz, where we dare to dive into the 128-bit address space wormhole. I'm Ed Horley.
And I'm Scott Hogue. On the show, we discuss all things IPv6, strategy, design, deployment, and operations.
And I'm Tom Coffeen. We've spent 20 plus years working with the IPv6 protocol. We run a consulting firm where we get IPv6 working for our customers.
And we're here to share some lessons learned and how to avoid common mistakes. We're glad you joined us today. Today, we're going to be talking about ICMP version 6 as part of our IPv6 basic series. So I think we just wanted to kick it off with, doing the obvious thing, which is comparing it to IPv4 and just regular ICMP and all the goodness that comes along with that, which I'm sure all our listeners are super familiar with ICMP and how that works. I'm sure everyone could rattle off every single type in code for IPv4, and we expect no less for IPv6. Let's talk really quickly about maybe what the function of ICMP is, and then we can compare and contrast that with just ICMP version 6. I guess just actually describing what ICMP stands for, which is Internet Control Message Protocol, which is what we use to basically do signaling effectively for IP. And I think that's probably the simplest way to describe it. I don't know.
It's like an administrative function where you can test reachability. It can give you error codes, related to a lack of reachability. You're familiar with ping, sending an echo request and getting back an echo reply, or you make a TCP connection and then you get back a destination unreachable or port unreachable or administrative unreachable. There's different types, and each type has a subcode that gives a little bit more clarification about what kinds of a error message or a function, test is being performed. So it's kind of this control protocol.
Yeah, I think it fits into a couple different functional areas. There's also capabilities of just providing like a little bit of error and messaging. It sort of feels out of band, but it's really in band. Mm-hmm. It's sort of a mix across the board. Anyway, that's our rudimentary, welcome to ICMP. I guess we should start with where it fits in IPv6, because it is slightly different. And I guess the major difference is, besides the fact that one is for IPv4 and one is for IPv6, is the fact that those types and codes that we use in both of these is actually different. So even though they may have similar functions across ICMP version 4 versus version 6, the type and codes are actually different, which of course, just to make your life that much easier, you have to remember different ones and what you're filtering for and how you're using them and everything else. I don't think that's super important, except for those that may be running firewall policy rules that actually have to maybe know those in order to determine what's an echo request or an echo reply or other specific things that they might be wanting to filter on, or maybe rate control or do control plane policing or something else like that. You might want to actually know those in order to understand what you're doing on your network. For most of us, I think you can look them up when you need them.
I think the other thing with V6 is we're kind of obligated to have a handle on them based on how they show up with neighbor discovery, which we'll talk about later in the episode. Since we don't really have an equivalent of that in IPv4, when we certainly have ARP, which, the IPv4 equivalent to the extent that it is. But I don't know that we're sort of on the hook to know as much about what's going on under the hood with the types and codes with V4, whereas with V6, with neighbor discovery, it's kind of an integral part, which again, we'll get into in a bit.
Yeah, because with IPv4 are really a separate function than ICMP, and it uses, LAN-based broadcasts to create that binding between IPv4 address and link layer address. And then in IPv4, we have IGMP, which is a separate protocol for multicast group membership.
Right.
Where in ICMPv6, it's all in ICMPv6. The host discovery, we call it neighbor discovery protocol, binding a v6 address to a link layer address. The group membership is performed with multicast listener discovery, which is an ICMPv6 set of types. And then neighbor discovery is a set of ICMPv6 types in IPv6. So with IPv6, we just have the one ICMPv6 protocol for neighbor resolution, multicast, and all the other functions, and ping.
And ping, yeah. I think just from backing up from a high level basis, just for sort of expectation, I think many people who operate sort of V4 networks today just think, oh, I'm never going to allow any type of traffic of ICMP from the public internet into my network, or from my network, maybe I'll allow it out for certain things. Maybe even if I'm running quote unquote a secure network, I'll turn ICMP off because I don't want people to do discovery of some type, right? Based off of that. So I think there's a lot of maybe misconceptions or maybe conceptions around V4 that ICMP is like a bad actor or something you shouldn't use, or you should only have it turned on for your internal network, but you shouldn't be doing the stuff externally. I don't know if that's a right read on that or not, but I certainly get that impression.
Yeah, I think some organizations, and rightfully so, may completely filter ICMP for IPv4 at their internet perimeter. Like no one should be pinging me. I shouldn't be pinging anyone else. And so they, wholesale block it. With ICMPv6, we have so many message types, and it's really integral to the end-to-end functioning of IPv6 communications. It can't be wholesale filtered. So you would need to learn these ICMPv6 types if you were going to do granular filtering, allow these, deny these. And there's an RFC, recommendations for filtering ICMPv6 messages and firewalls, RFC 4890, that goes through and gives the proper guidance for what to filter and what it describes as in transit. So transiting like through your internet perimeter, and then recommendations for filtering on a local LAN. On a local LAN, there's so many ICMPv6 messages that are required. It's almost not worth trying to filter because it's such a huge list. But across the perimeter, you can be more specific, and the RFC gives you the right guidance.
Yeah. And for anyone who's operating maybe anything that looks like a transit or a backbone or a service provider network, you're definitely going to control what sort of messages are occurring because you want to sort of prevent abuse of your resources, because there are things that your routers are going to have to do in response to certain sets of messages. So you don't want to give bad actors the capability to exploit your generosity of replying back properly in IPv6.
ICMPv6 can be abused just like ICMP. And we talked about, IPv6 and large scale reconnaissance, and it could be used as a DDoS attack. People could use it to map out your network. You do want to be specific about filtering at your internet edge. So that's why this show is particularly important to know exactly what you should or shouldn't allow.
Yeah. So let's talk about what ICMP uses first and foremost within IPv6. And so it uses effectively process under the extension header. Finally, something that's using the extension header. Why you can't get rid of extension headers for all those people out there. Extension header 58. And probably the two most sort of groupings of types that are going to be interesting for people, I guess, is starting off the simple one is ping, right? So 128 is an echo request and 129 is an echo reply. Hope I got those in the right order.
Yeah. That should be familiar to everybody.
Yeah.
I can't reply before you request. So,
and the numbers come in the right order. So you think 128 first is the request and 129 is the reply. So it's in that order.
Yeah. And then we have another grouping, I guess, that we can talk about next, which sort of introduces sort of the adjacent part of ICMP. ICMPv6 uses a lot of multicast in IPv6. And we have a whole process to sort of do multicast listening as part of sort of the whole process of like neighbor discovery as a general bucket. And there's a bunch of, starting from 130, there's a whole sequence of multicast listener processes. So 30, I think 131, 132, I think they're all like multicast listener. I can't remember the order for all of these, you guys. I apologize.
Query, and then the report would be next. So 130 would be a query, 131 would be the report, and then 132 is a done, like a leave message, equivalent to IGMP version 2.
Right. So those are all going to fit in that process. So I'm assuming most of these are going to multicast addresses of FFO2 in scope, right? On link FFO2 : and I'm assuming if you're doing a query, you're going to do all nodes. So that would be a FFO2 : 1. And then I guess if you only have to direct a listener to disjoin, it would be a specific address for that. Probably the routers. :
16.
16. Okay, cool.
you're getting some bonus multicast with this episode.
Yeah.
And then that extends down into the whole neighbor discovery process, right? So like router solicitations, router advertisements, neighbor solicitations, neighbor advertisements, all of those fit in the same general, like, hey, I'm trying to communicate on the wire and I don't necessarily know who I'm communicating with, right? Hence, I need to solicit for who the router is, or the router sending a router advertisement, and I want to notify all the nodes on a particular LAN segment that I am the router. So you're going to use ICMP version 6 to a multicast address, and you're going to use a particular type to do that. I think the router solicitations, you guys are going to have to correct me on this, 133, I think the router solicitation comes first, and
Yep.
34. Okay, I got that in the right order.
Yeah. The node solicits the routers first, and then the router
response
sends the advertisement second. So it's a 134.
Yep. And then same thing for no router involved. I'm just a host or a node on the network, and I want to know someone else on the network. So I'm going to use a neighbor solicitation. We've talked about this in previous shows, but never in a basics, but a solicited node multicast address, right? We're going to request specifically to talk to a host, and we're going to use their solicited node multicast address so that we don't interrupt everyone on the wire, right?
Mhm.
That's the whole purpose, is we don't interrupt everyone because they're only listening for the last 24 of their address. We're only going to interrupt people that are listening to the same 24. It's not a guarantee of complete uniqueness, but it's guaranteed to 24 bits, which is pretty good.
Close enough.
Close enough in the
Yeah.
grand scheme of things. So that's
So the NS is 135. So
Right.
you do the solicitation first, and then the neighbor advertisement is 136, comes second.
right. Perfect. So we've covered through those. And then I guess the next one that's probably most common would be a redirect message, some sort of redirect like, hey, there's a better place to get to the destination you're trying to reach, right? So maybe you have two routers or another particular firewall host that says like, hey, there's a better route to get someplace. I'd like to redirect you over to that location. And that's a 137. Quick sort of rundown through it. I guess technically neighbor solicitation and neighbor advertisement would feel like a ARP replacement. Does that seem right? That the neighbor solicitation, neighbor advertisement, that's the same sort of function as ARP.
One of the things it does, right? The address resolution, essentially. But then you've also got duplicate address detection.
Yeah, prevents address overlaps. I wish IPv4 had that, because we have such dense IPv4 addressing. You often have collisions
Right.
in V4 addressing. You wish you had duplicate address detection for V4.
Hello, podcast listener. Did you know you can get even more nerdy podcast goodness? Check out Heavy Networking, a weekly conversation about routing, switching, WANs, LANs, data center networks, and more. Each episode features network engineers and industry experts going deep on existing technologies, as well as looking over the horizon to see what's coming next and how to get ready for it. We also offer insights and tips on professional development and career advancement. From access control to zero touch, from the CCNA to the CCIE, Heavy Networking is the podcast for network engineers. Listen wherever you get your podcasts.
Yeah, and avoiding that behavior where, you just basically lose connectivity. I think maybe that was something that showed up, rather you won't get an address at all. The operating system just gives up.
Yeah, if you're not doing EUI64, it's just going to generate another random. I guess the only place that would be bad would be maybe link local, but I'm sure that just tries. You got to the 64th tries.
It tries 3 times. If dad fails 3 times, it gives up and shuts down IPv6 on the interface. I've seen that with cloning virtual machines. They all start out with the same Etsy machine ID. They use that as the seed to compute their link local address. That's the first address they start with. They do duplicate address detection. They all match each other because they're clones of each other. So they all back off, recompute another one, and they all recompute the exact same second link local address, conflicts again. They try a third time, fails again, then it gives up, shuts down V6.
That's really sad. You enter the world with high hopes, and then 3 failed tries later, you realize you're just like your clone and completely optional.
Yeah, because it uses like machine IDs and stuff like that, right, to generate the randomness of what they're building for the address. So I think you definitely have to do a sysprep for Windows machines in order to avoid that same problem if you're using like virtual machine and golden image or something like that in order to get something different. I guess maybe in that case, having something tied to EUI64 because each one got a unique MAC address might be a plus in that particular situation. I don't know.
Hopefully the listeners at this point are getting some sense of how IPv6 is so heavily reliant on ICMP version 6 because everything that we're talking about under the hood is leveraging ICMPv6 to make it happen.
Can't live without it.
Can't live without it. I think it's really important. As a note, you will see if you're used to doing packet tracing on a particular LAN segment and watching the traffic go across, when you see V6, you will see exponentially more ICMP traffic than you will see in V4 as a general rule of thumb, just for those that like to fire off WireShark and take a look around. I think you'll be maybe pleasantly surprised about all the message types and how clearly things are sort of laid out. So I think it's actually easier to figure out what's going on than the equivalent in V4 with trying to figure out what's going on with ARP and everything else. Not that WireShark doesn't make that relatively easy to figure out, but still it's relatively well laid out and easy to sort of determine what's going on.
Yeah, it's a good way to learn ICMPv6, just open up Wireshark, start to capture packets on your local LAN interface, and then in the display filter, just type in ICMPv6, press return. Simple as that. You'll only be looking at ICMPv6 messages. There aren't many of them, and so you're not going to be inundated with a flood of information. And you can look through and you'll see multicast listener reports and queries. You'll see the NSs, NAs, and you can learn the little types, by looking through the traffic. So that's a good way to look at that. With Wireshark, you can look at a specific type like ICMPv6 dot type equals 134 and look for your router advertisement. So that would be the display filter.
Yeah, that's cool.
Mm-hmm.
Well, I guess there's another function for ICMP that we had talked about. This was sort of the when we're typically doing stuff around ping and echo request, echo reply, there's an additional function that sort of fits in there that's a little different for V6 than V4. And it really has to do with, sort of the size of payload of what we can send back and forth between two hosts. And in IPv4, we assume the network's going to do all sorts of fragmentation and other functions for us in terms of handling if maybe the MTU size isn't appropriate between my host and the far destination that I'm trying to reach, and vice versa, from it back to me for communicating. But in IPv6, they made a big structural change. And I'd say it's pretty significant, right? That they did not allow the networking routing nodes or firewalls to go ahead and fragment on your behalf in between on the path. And so you need to sort of have some mechanism or some way to determine the maximum size of a payload you can deliver from your host to the far destination that you're trying to reach, and vice versa for it to do the same to you. And this process is called path MTU discovery. It's a way to be able to discover the maximum transmission unit that you can actually deliver between two hosts. And we leverage ICMP version 6 to be able to do this. So I guess we can talk a little bit about that. And this gets back to that original conversation about what we started off with, about why you might have different sets of rules for where you can't follow your standard default, IPv4 rules of blocking all ICMP related traffic. That's just going to be bad for you in terms of performance if you do that and you don't have path MTU discovery within your network to the outside world or even internally, right? I think it'd be particularly bad if it was internal, because you're going to have a lot more problems just in terms of probably getting the performance that you would expect out of your network.
So with ICMPv6, the functional messages and the types that we talked about start at 128, echo request. And the error message types are 1, 2, 3, and 4. And so those are likely the ones that you may want to allow, in transit through your internet perimeter, because they have an error code that you would want to be communicated across a WAN. And so number 1 is destination unreachable. Number 2 is packet too big. That's what's used for this path MTU discovery. 3 is time exceeded, and 4 is parameter problem. With ICMP for IPv4, although the error codes are all intermixed with everything else, all the other types, with IPv6, we've kind of put them all, 1, 2, 3, 4, very nice and neat at the low end of the type list.
Yeah, I think the packet too big message is probably the most important, because that's what tells you, hey, I have an interface on my router on one side that's unable to accommodate the message that you're trying to send. Please go adjust yourself accordingly. And then hopefully I'm providing the parameter information back that says what MTU I will allow through that interface. That's the normal. This also causes a weird thing where you have to let some random router who your traffic may be going through to connect and reply that message all the way back to your originating host, which may not be the destination of where you're trying to get to. It's just along the path somewhere. So this maybe doesn't feel great to the security team of like, oh, some weird random router along the path is just going to send a ICMP type 2 message packet too big back to me. Isn't that something I should be concerned about? Should I even allow that? And in this case, yes, you need to allow it.
In our internet scanning show, we did talk about how the packet too big trick can be used as part of WAN reconnaissance. So there is a small risk there.
Yeah, for the data gathering side, right? In terms of sort of figuring out what's what, which, from a trade-off perspective, there's other ways for folks to also scan and look at your network and have an idea. So I don't think it's appreciably bad. And there are definitely best practices in regards to rate limiting and controlling how much. You don't need to have a crazy number of messages coming back from a router for every single thing. And eventually host operating systems just give up and start backing down to the lowest common denominator, which is 1280 anyway.
Yeah, it's 1280 MTU.
Right. So you always have that bottom floor IPv6. It just won't function below 1280 anyway. So if you don't have that available, you're not going to get anywhere from point A to point B. So it doesn't really matter. So I think that's maybe the floor portion, and the ceiling is just whatever you want to send. If you're running it like internally within your data center, you're running jumbo frames and everything else, and you're setting your MTUs high enough for passing that payload, you definitely want everything responding back so that you know you can take advantage of all of that sort of across the board within your internal network, right? Those would be the big things. I think we probably covered most of the basics around ICMP version 6, right? I think we covered effectively what it is. We've covered the fact that it's an extension header, the common types, the fact that it leverages multicast, and the whole path MTU sort of discussion, which I think is probably encapsulates a good portion of ICMP, at least at the base level, for what the audience might need to know. I don't know. Is there anything else that jumps out to you guys, or?
Yeah, just seconding Scott's comment about firing up WireShark on your local network. If you got IPv6 enabled, you'll definitely see some interesting traffic by putting in that display filter that zeroes in on neighbor discovery and, well, just zeroes in on ICMPv6. You'll see neighbor discovery packets. You'll see MLD, all sorts of interesting things. And it's a good way to get familiar with it.
Yeah. And then we'll jump off from what we talked about today in a future basics show where we'll talk about neighbor discovery a little bit more. So we've just kind of touched on what we'll cover in a future show.
Right. We sort of hand waved on neighbor discovery. We just talked about the ICMP types, but not really what's going on there in any detail about how it actually works for neighbor discovery, which includes router solicitation and also for neighbor solicitation and neighbor discovery, and fits under that umbrella. Well, awesome. Well, we hope this series is helpful. So please let us know. If you can go to packetpushers.net/FU, and the FU is for follow-up, and just send us a note and say like, hey, really like the IPv6 basic stuff. We would appreciate it. And any feedback you have about it, we would love to hear.
Also, on packetpushers.net, you'll find a range of deep dive technical podcasts for IT pros, including heavy networking, heavy wireless, and day 2 cloud.
There's a whole lot more on the Packet Pusher site as well, such as tutorial videos and a networking job board to help you find or fill your next great role. So whether you're deep in your career or just starting up, Packet Pushers is the place to go to grow both your skills and your personal network.
So long, and until next time, we'll see you on the IPv6 internet.